Good morning, everyone. The last topic in the first module is boundary conditions. Okay, so we have the last topic of boundary conditions. So now I am going to start off for the two dimensions. Say you have a given body. I'm going to consider just a small piece in this body or an element. I can call this as an element. This is the surface of the body, the external surface of the body. Okay, if I zoom in this element, it will look something like this. Okay, fine. Let me consider an outward normal. This is an outward normal. I'll call this as N. Normal because it makes an angle of 90 degrees. Alright, I'll resolve it into respective x and y components. This is fy and then this is fx. Let us consider that the normal makes an angle of alpha with respect to your horizontal and it makes an angle of beta with respect to the vertical. Let us write the stresses that are going to be generated. In the y direction, we have sigma y, and then in the x direction, we have sigma x. Coming to the shear stresses, we'll have tau xy followed by tau yx. Alright. So what have we done? An element at the surface of the boundary must be in equilibrium. Okay, we have considered an element and this element has to be in equilibrium. For the surface elements, differential equations will not be developed. Hence, algebraic equations of equilibrium have to be used. I'm going to use algebraic equations of equilibrium. Now, Fx and Fy are the components of the external forces on the boundary surface. Alright, if I consider the equations of equilibrium in x and y direction, that is summation Fx is equal to 0 and then summation Fy is equal to 0, then I can write something like this: Lx into sigma x plus Ly into tau yx is equal to Fx. This is the first equation, and then Lx tau xy plus Ly sigma y is equal to Fy. What is this Lx, Ly that I have written is? Lx is nothing but cos alpha, Ly is nothing but cos beta. These are the direction cosines of the normal n. Theta means direction, so an angle means direction. Cosine, we have used cos over here and it is with respect to the normal that you have drawn. So direction cosine of normal n. This direction cosine Lx and Ly are going to be positive if the corresponding components of n in x and y direction are going to be positive. Okay, so these two equations are for two dimension. So these are known as boundary conditions for two dimension. If you want to write the same thing for three dimension, I'll generalize it and write it for three dimension. Then we'll have fx component, fy component and then fz component. Similarly, I'll be considering the three equations of equilibrium, that is summation fx is equal to 0, summation fy is equal to 0, summation fz is equal to 0. Hence, I can write Lx sigma x plus Ly tau yx plus Lz tau zx is equal to fx. And then Lx tau xy plus Ly sigma y plus Lz tau zy is equal to fy. Last, Lx tau xz plus Ly tau yz plus Lz sigma z is equal to fz. Now these three are the boundary condition equations for 3 dimension. I can write Lx is equal to cos alpha, Ly is equal to cos beta, Lz is equal to cos gamma. The third angle with respect to the normal and then the z-axis. So if you can see the trend over here, if I want to reduce all the 3 equations in the form of a matrix, I can definitely write it as sigma x tau yx tau zx, then tau xy, sigma y, tau zy, then tau xz, tau yz, sigma z into Lx, Ly, Lz. This is equal to fx, fy, fz. Okay, we have reduced it in terms of a matrix equation. Yes, this is the boundary condition for 3 dimension.